In problem 34 in section 15.3 on conservative vector fields, we have a field given by f equals y x, and we want to integrate along a curve that is a circle of radius 8 centered at the origin, oriented counterclockwise. So we can parameterize this circle as 8 cosine t, 8 sine t. Then we have radius 8, center at the origin, and indeed this is oriented counterclockwise. Now with this parameterization, the velocity is the vector negative 8 sine t, 8 cosine t. So now we can compute the integral along the curve of f dot dr. With this parameterization, t goes from 0 to 2 pi, and in place of y we have 8 sine t. In place of x we have 8 cosine t. And we're going to take the dot product with the velocity, negative 8 sine t, 8 cosine t dt. So when I take the dot product, I'm going to get negative 64 sine squared. So we get negative 64 sine squared t. Then I have 8 cosine times 8 cosine, so plus 64 cosine squared t. And I can bring out 64 so that I'm integrating cosine squared minus sine squared. Well, if you remember your double angle formulas, cosine squared minus sine squared is the same thing as cosine 2t. Cosine squared minus sine squared is cosine 2t. And this allows us to integrate this simply because we have 1/2 sine 2t. So there's my 64, and then I integrate to get 1/2 sine 2t as t goes from 0 to 2 pi. Now, sine of 2t takes on the same values no matter whether you plug in 2 pi or 0. So this whole thing has an integral of 0. Now notice that this curve is a circle. In particular, it is a closed, smooth, simple curve. It's closed, it starts and ends at the same point, and it's smooth. So f is a conservative vector field because it has a potential function for which it's the gradient of. What is yx the gradient of? Well, if I integrate y with respect to x, we get xy. And notice taking the partial derivative with respect to y gives us x. So it's very easy to see that a potential function for this field is xy. Again, notice partial derivative of xy with respect to x is just y. Partial with respect to y is just x. This means f is a conservative vector field, and we know that whenever we integrate conservative vector fields over smooth, simple curves, closed curves, we get 0. This explains this final result.